My name is Danny Volkind, and I'm the CTO and co-founder of UnifabriX. In this video, I'll show you a recap of our world-first demonstration of UnifabriX CXL-based Smart Memory Node that took place at SC-22 in Dallas, Texas. So let's talk about our system setup. In this setup, we have two UniFabric Smart Memory Nodes connected to two Archer City platforms. Archer City platforms are Intel pre-production platforms supporting the Intel Cepha Rapid Xeon CPUs, which in turn support CXL 1.1. So all these connections are CXL 1.1 Gen 5 by 16 connections, which supports roughly 128 gigabytes per second of bidirectional bandwidth, or roughly 1 terabit per second of bidirectional bandwidth. Between the UniFabric Smart Memory Nodes, there's a fabric that supports CXL 3.0 semantics, meaning that these two Smart Memory Nodes are able to interact and connect using CXL 3.0 semantics. I will start the demonstration with running HPCG, which is a widely accepted HPC test bench on one of the Archer CD machines. In this case, what you will see is that not only that the performance are not degraded when running over CXL, we are actually able to accelerate performance when running with our Smart Memory Node. My second demonstration will be our SSD over CXL. In this case, I will expose some of the capacity of the Smart Memory Node as a standard NVMe device over the same CXL connection. This device will expose itself as a standard NVMe device to the platform, and we will run standard FIO testing to explore its performance. The third demo that I'm going to show you is a memory pooling demo. And in this demo, I will show you the Smart Memory Node's capability of allocating and deallocating memory to platforms on the fly while the platform is running without the need to reboot the system when changing the amount of memory that is exposed to the platform itself. This is our demo window. On the right side, you can see three shell windows in which we can look at the workload's output while we are running. We'll start by running HPCG. We are going to speed up the video a bit. While HPCG is running, we can look at the output on the lower right shell window. You can see that we're using the open source reference code for HPCG version 3.1, and you can also see the problem parameters that we're using. HPCG will be invoked multiple times. In each time, we will increase the amount of processors working on the problem. On the left side of the screen, you can see our dashboard, which draws a graph of the relative performance as a function of the amount of cores working on the problem based on the real-time results from the HPCG runs. We are expecting to see an increment in relative performance proportional to the amount of cores working on the problem itself. The desirable behavior in terms of performance versus cores would be to get a linear increment in performance proportional to the amount of cores added to work on the problem. For relatively low core amounts, we can see this kind of linear scaling in performance. As more and more cores are added to work on the problem, we see a gradual drift from the linear trend line. The drift away from linear scaling of performance is mainly attributed to the effects of loaded latency, as cores are waiting for longer periods of time for accessing memory. This drift worsens as more and more cores are added to work on the problem, up to a point where we get to a plateau in terms of performance. At this point, we have exhausted all the memory bandwidth of the system, and adding more cores to work on the problem will not yield any additional performance. As you can see, once we are getting to a point where there's a bandwidth problem, two identical runs are invoked for each data point. One run will only use the local memory, and that is the lower graph that you are seeing, while the other run is dynamically interleaving the data between the memory on the system itself and the memory exposed by the Smart Memory Node, which yields us an additional bandwidth, immediately translating to additional performance of the workload itself. The unique ability of the Smart Memory Node to expose both bandwidth and capacity to the system enables cores that were previously stranded to be fully utilized and increase the overall performance of the workload. When we are getting to the final measurement point, we will see that we are getting a performance boost of approximately 27.5%, while the core utilization increases by approximately 100%. We have now switched to our SSD over CXL performance benchmark dashboard. We will start by running a standard bandwidth test. Similar to the HPCG runs, you can see the FIO command and output on the middle shell window on the right side, while on the left side you can see the graph drawn on the dashboard showing the real-time results collected from the FIO output. As you can see, we are getting approximately 33.3 gigabytes per second of bandwidth. Also note we are using 2 jobs and an I/O depth of 64. The next test is a latency test. In this case, we will be using a single queue with an I/O depth of 1 using a poll queue mechanism. Also note, this is a standard 4K IOP random read test. As you can see, we are getting a pretty stable completion latency of 2.34 microseconds. Our 4.9 tail latency, not shown in this test output, is around 3.5 to 4 microseconds. Our last SSD over CXL test is an IOPS test. This standard 4K IOPS random read test uses 20 jobs with an I/O depth of 256. As you can see, we are getting an average IOPS measurement of 7.3 mega IOPS, with peaking at 8.1 mega IOPS. The unique ability of UnifabriX Smart Memory Node to expose an ultra-fast, ultra-low latency standard block storage device enables customers to use storage devices on demand over the same CXL connection, exposing memory. We have now switched to the memory pooling dashboard. On the upper right shell window, you are able to see a standard NUMA-CTL output showing the memory exposed to the system by the Smart Memory Node. As you can see, we can select any value of the available memory to be exposed to the system, and when we hit on the Allocate button, the memory is online by the system itself and reflected to the system. On top of adding memory to the system, we are also able to reclaim back memory to the Smart Memory Node. In this case, memory will be offline by the system itself and be released back to the Smart Memory Node. Note that memory allocation and deallocation occur on the fly while the system is running, and we do not have to reboot the system to get it reflected and used. Concluding our demonstration, UnifabriX Smart Memory Node enables unparalleled functionality with existing CXL 1.1 supporting platforms. These functionalities include memory pooling, enabling dynamically expanding and reducing the amount of memory exposed to the platform. Memory bandwidth expansion, enabling workloads to run faster by enabling underutilized cores to access additional memory bandwidth. Ultra-high bandwidth, ultra-low latency, standard block device exposed to the platform on demand, and plenty of additional features that will be exposed in the future. All are run over the same CXL cable or the same unified fabric. For more information, please visit www.unifabrix.com.